Okay, record. Okay, record the program already. So your name? Lenai. Lene. Lene, yeah. That's okay. I expect someone late already. Yeah, I expect that before. Yeah. Okay. Yeah. So now when we got the data, the number, even you have got the like a male or female, like this, you have to change to the number. So that you create that by yourself, but you need to know. You code it, but you need to know which number is what does that mean. For example, I create female like a 0 and male like a 1. That depends on you. You can create anything like that. For example, someone may create a woman as a 1, man as a 0. That's okay, no problem. Just the symbol, just the number. That you need to know the meaning, and then I say the other variable, for example, the opinion or the aptitude test or something, the other variable. So you think about the opinion, the opinion to the garbage usage in the city. This is one variable, and then when you ask them the opinion, and then for example agree disagree or something like this, and you need to change to the number. Change to the numbers like that, 5 4 3 2 1, something like this. Mm-hmm. Uh, when you collect such as this data from sample, for example 200 sample, and then you need to key in the program to analyze, key number, key in, enter the number to the program. For such as SPSS, you key 5 4, it depends on the real answer. When I would like to say that you need, before you analyze it, you need to clean it. I would like everyone to remember the way to clean it we call outlier, OUT. You need to do that first. Outlier, you need to clean some data that exceed the normal, delete it or change it. If you know what is what is it should be, you change it. If you do not know, delete it. Yeah. Sometimes is mistake. Why? When you type, you key in, you enter the number to the program. For example, I have experience like I would like to key in 3 and then enter 4 and enter 3 and enter 3 and enter. I key 3 and enter double 3 in one cell. So the result would be 33. No, that's wrong. That is not true. When before I analyze the data, I need to clean it. Outlier.
In this video, we will discuss how to deal with outliers, data points that seem to be significantly different than the rest of the data points in a distribution of data. So what are outliers and why are they important to us as far as helping us analyze our data? Well, these are data points that appear to be significantly different than the majority of the data points. We're usually being able to identify those either in a scatter plot or in a histogram or through functions in SPSS that will give us an idea if we have scores that are higher or lower than the majority of the scores. Now we can identify those either visually, as I mentioned, but the most effective way is the outlier labeling rule or labeling technique, in which we're using the quartiles, the third and first quartile of the data set we have, taking that difference between the two quartiles and multiplying it by 2.2, and then either adding that value to the third quartile or subtracting it from the first quartile value in order to determine boundaries for outliers. Once we've identified those outliers, if we do have any, we need to try and figure out what we're going to do about them. And why that's important is because these outliers can significantly skew data from a normal distribution. We can have just a single score that may pull the mean in one direction or another that will then misrepresent the data. If we have data that no longer represent a normal population or a normal distribution, then that limits our choices as far as ways we could manipulate or analyze that data. And a normal distribution being one of the primary assumptions we have when we do parametric statistics. Because of this assumption of normal distribution for parametric statistics, if we try and do parametric analysis techniques using skewed data or data that is not normal, that would significantly affect the accuracy of that technique, and we would be testing our hypothesis using a p-value that probably will not reflect any true differences that might be there. This can also affect how well a sample then represents the population. If our sample has some outliers, but these outliers are not typically present in the population, then our sample no longer represents the population, and any inferences that we make during hypothesis testing will be false, and that will then limit the external validity or the generalization of any results that we might have. So we've talked about what outliers are, why they're important, and why we need to try and identify them. Now let's talk about some of the different techniques we have for dealing with them. Now there are two techniques that are considered to be the most common, and they're techniques that are used in two different kinds of situations. And the first technique is called trimming. And this is where we're basically eliminating data points from the analysis based upon several possibilities. In other words, things that made them outliers or reasons they might be outliers, which would then allow us to feel comfortable with or compel us to then trim them from our distribution of scores. And this is usually done when we have data that is out of range. In other words, if we're measuring a certain value and the highest possible value is a 10 and we have a score that's an 11 or a 12, then we know that that's not possible based upon the measurement technique we were using. So that data is invalid, it's out of range, or we have a situation in which there is a data entry error. In other words, we're measuring body fat percentage and we have an entry that reads 360%, then we know that's some sort of an entry error. The next is if we feel the data is biased in some way and biased through measurement error. Perhaps there was a measurement error in individual data points that were collected, or maybe in a series of data points that were collected, there was some sort of measurement error. Maybe the measurement tool wasn't used correctly, or maybe the equipment we were using to measure a certain variable was not calibrated. If we suspect that there was any measurement error or the data was biased in some way, then that's another reason we could trim the data. And then lastly, if we feel the sample is biased, in other words, there might be subjects in the sample that either shouldn't be there because of some sort of sampling bias, or that they are there and they no longer represent the sample we expect to. So let's say we've collected data and we assume our sample is under the age of 65, and we might have some subjects that are over the age of 65 through some sort of error, then our sample is now biased. So very often when we have these situations, like data that's out of range or missing, or there's entry errors of some kind, and we don't have the raw data available, we can't go back and fix those. If we have a situation in which data is biased or there's a measurement error, again, we typically cannot go back and re-evaluate or re-measure those subjects. And then lastly, when the sample is biased, we don't want to include those subjects in our sample because that would make the sample non-representative. And so when we have those kinds of situations, we basically eliminate those data points from the analysis. We throw those data points out. In other words, we trim them from the data set in order to eliminate those possible outliers. Now the other technique is known as Winsorizing, and this is done in a situation in which there has not been a mistake made, but it's a situation where it's a valid or legitimate score, but it truly is an outlier. It's higher or lower than the majority of the other scores. And so when we have small amounts of scores that we consider to be legitimate outliers, we can transform those scores by assigning them to the next highest or lowest value found in the sample that we consider to not be an outlier. So if we had data on salaries and the majority of salary data was less than $100,000, but we had one data point that was $200,000, and that's a legitimate score, but it's a true outlier, what we would then do is transform that score to 100,000, which is the next closest value that is found in the sample that is not considered an outlier. Now, it's recommended we do this for very small amounts of scores, typically only 2 or 3, if we have that situation where we have 2 or 3 outliers and they're legitimate scores. We can Winsorize them and feel that we haven't really affected our ability to analyze the data. But when we have larger numbers of scores, then we typically cannot Winsorize. So let's go run through some very quick, simple examples. So let's run through an example of trimming. So as we can see here, we have some data points, and the majority of data points are clustered pretty close together. And then we have 2 data points that appear to be significantly higher than the others at both ends of the distribution. And so in this case, we determine that these have been outliers through whatever method we're using. And what we would then do is just eliminate them. We would trim them. And so now our distribution would have those 2 scores eliminated. Now it would be a smaller distribution, a smaller sample, but we've now eliminated those outliers and our distribution is more likely to be normal as opposed to being skewed. Now an example of Winsorizing, here's that same data set that we had before. And let's say we know that the 2 and the 22 are not mistakes. They're true values, but they're true outliers. So how do we deal with those? Well, we transform the 22 into a 14, which is the next closest score that's not an outlier. And we take our 2 and transform it into a 10, which is the next closest non-outlier score. And so our sample would have the same number of subjects in it now, but those outliers will be eliminated. And again, we're typically only going to do this when we have small numbers of outliers and we know that the values that we've collected as outliers are legitimate, unbiased sample data. Okay, so a few final thoughts as far as dealing with outliers and some of the different techniques that we've talked about. When we have less than 5% of our data points that we feel are outliers, again, using whatever standard or criteria we want to, if we've got less than 5%, trimming or Winsorizing the data will very likely not affect any hypothesis testing outcome that we do, and it won't significantly affect the p-value at which we are testing. If we have greater than 5% of our data set that may need to be trimmed or Winsorized, we need to be very careful about doing that. And in many cases, we want to try and avoid that situation. When we are trimming or Winsorizing greater than 5%, that could definitely affect any hypothesis testing outcomes and could certainly affect the p-value at which we're testing our hypothesis. So when we do trim or Winsorize greater than 5%, what that does typically is significantly reduces our sample size, which may then reduce the power of our analysis. It may also make the sample size less representative by reducing it in size, and now the sample might no longer represent the population as much as we intend, and that again affects the generalizability of our results. If we had close to a normal distribution of data and we start trimming more than 5% of it, that might actually create a skew, depending on where the trimming is taking place. It might not always occur at both ends of the distribution. It might occur at one end of the distribution, or it might be kind of scattered throughout the distribution, especially if we're talking about trimming, where we're trimming data entry errors or data that appears to be unlikely to be unbiased data. We could be affecting the normalcy of our distribution. It could now become a skewed distribution. So when we have those situations in which we've got greater than 5% that we feel like we need to trim or Winsorize, we probably want to avoid that for the 3 reasons that I stated. And we might want to consider transforming the data in some way, converting it to a different kind of alternate outcome variable. Instead of reporting pounds of weight loss, we might report percentage of weight loss. We might consider transforming the data using a method called bootstrapping, or we might have to use an alternative data analysis technique. Instead of using parametric data analysis, we might have to use non-parametric data analysis technique. So these are some things to consider as you look for outliers, as you think about how you're going to deal with your outliers. If we've got less than 5%, then trimming or Winsorizing is a perfectly acceptable way to do it. If we've got greater than 5%, we might need to really think quite hard about the pros and cons of trimming or winsorizing. In the description of this video, I've included some references if you'd like some further information about these techniques. And hopefully, as you do your data analysis, you won't have to do either of these techniques. But if you do have outliers, at least now you have some options on how you might deal with this situation.
First thing, clean the data. The second thing, before you analyze the data, you need to find out when you make decision which statistic you are going to use. Suppose we are going to compare two variables. You make decision to use t-test. You need to know what is the assumption of t-test. All kind of statistics have their own assumption. Assumption, that is important. Assumption, ASSUMPTIOM. Yeah, assumption. That's very important. Each statistic have their own assumption, different. Sometimes the same, but you need to see what is the assumption. Everyone need to check assumption. If it pass, assumption, all of assumption. That's important. If you ignore this and then you analyze, the program will find out the result for you, but it's not true. The computer program will analyze and show you the result, but the result is like a again assumption. Assumption. Yeah. So after clean the data, then you need to check assumption. If everything passed, that is the time you can analyze the data, and the data is very reliable. So the process to analyze the data, the first thing when you got the number, you need to clean it first. If it's within the range, use outlier checking, and then check if the assumption is passed or not. One assumption that I seen quite a lot is about normality, the normal distribution. SPSS will provide you the way to check normality, normal distribution. I have the video, but I will post later. Yes, please.
I was just wondering.
Yeah.
I mean, there are no rules here. I mean, if you see an outlier, you just could delete it like that. I mean, wouldn't it affect the integrity of your data?
No, if you not delete it, that it will affect the result. And if you we have, I will suggest you need to think if that possible. Sometimes when you ask people about age, how old are you, and now we know the sample could be age between 20 to 60 support, but someone just type 200, that just 200. Yeah.
Just an example. I mean, all of us.
Yeah.
I think if we took our ages, I think I would be an outlier.
Yeah.
So,
no, you need to think.
How
Yeah.
do we manage a situation like that?
Yeah. No, not just delete, only delete it. No, you need to, everyone remember. Just think if it's possible. Think first. You will find outlier from the program. The program will show you which one is outlier. Outlier is mean some data is out of the group. You know what I mean? The outlier is mean some data. Not normal. Yeah, not normal, right? Not normal. Some data, not all data. Just some, 2 or 3 or 1. Just not normal. Not normal. It may be it's higher than someone else quite a lot, or lower quite a lot. Everyone remember, you need to think is that possible. If you think that's possible and that you believe that's true, that one you go and collect the data. That one very old. He stay in a house very old, and then the data that could be right. That could be true data. That could be acceptable. Leave it like that. That is the real. That is the truth. That is the truth. But most of that, when I see outlier, maybe is not something mistake. But if you believe that is the real data, do not delete it. Leave it like that. Yeah, leave it like that. Yeah.
Even if not deleting that outlier would say
yeah, we affect some result. We
but screw up the entire.
Yeah. We screw up the normal curve. Yeah, we screw up the normal curve. But that is the problem. If something like that happen, that mean when we select the sample, that is not like a perfect selection, because we collect the data from like a teenager, but what happened we do not know. Just the parents come to answer, and then we have got something different. That is the outlier, but that show that explain us something. Yeah, you need to think about that. You can make decision. Actually, we not very strict about outlier. We delete it. When I do like when I suggest my student in Thailand, I tell him or her, delete it if you think that it will create the problem. Sometimes it create the problem. Outlier, you shouldn't worry too much, because like we collect the data from 200 samples, but one outlier delete, and then we have 199, and just we delete one, we still have 199. Yeah, yeah, yeah. And if the 199 make a good normality, a good, the other thing is good, just delete one. But that's okay. Just delete one or two. That's acceptable. I told my student, don't worry too much about it. When you can find some outlier of the data, you just delete it. Yeah, but however, I told you already, if the mistake from typing or something, edit it, correct it. That is something wrong. Okay. Another assumption, you need to check each one. Each statistic will have their own assumption. And then the next thing, when you are a student, you need to learn which statistic you are going to use. Which statistic you are going to use to analyze the data. And this course until the end of the semester, I will tell you every week when we would like to analyze some kind of statistic like this, which statistic we are going to use it. I will tell you every week. When we would like to compare, when we would like to find out the correlationship, or when we would like to find out the influence from one sample to one variable to another variable, and we are going to use which statistic. You don't need to remember the formula. I don't need that. That's old style. Now we have computer. We don't need to remember formula x1 plus x2 plus x is something like that. No, we don't need that. But I expect you to understand why you are going to use this kind of statistic, and I would like you to use the right one, the right statistic. Okay. This is the process of analyze the statistic, and it is in my final examination too. Not only this, I would like you, my student, to explain the result, display the result. When you analyze statistics already, you will get the result, how to present the result to the audience when the people read your output, your outcome, your report, and how can you present the report to the audience. That I expect everyone to do that in the end, the final exam. That make the conclusion of why you do what is the result, and can you explain what is it, something like this. Yeah, you can see the sample from the journal or the research. That is the best example. You can see, yeah. Yeah, the report from that. That's the same way. You can use graph, you can use table, you can use, normally you use table. You can use graph or table or something to present the number, and then you make the descriptive word under the table, something like that. So that's it, the overall that I expect all of you to learn and to know, to have that kind of ability. This is necessary for all of you to do your research. I think if you select to do your research with the way we call quantitative research, you need to have this kind of skill. Otherwise, you cannot analyze your data. Someone may say, I will pay money for someone to analyze the data for me. That's possible in Thailand. Someone do that, but at least you need to explain your supervisor when you before you submit your finish. You need to in Thailand we have to show your knowledge to the supervisor, external supervisor and internal, and someone else explain. They ask you, they will ask you what kind of this, why you shoot this one, what happened, and something like this to test you if you understand that. So yeah, I would like everyone to understand that. You need it. This is the way to analyze statistics until now. Anyone would like to ask something? Some question? Ronel?
Yeah, Sir Sean.
Yes, Eileen.
Can I ask something?
Sure, you can ask.
Okay. There is an instance within two agencies, like example, since we work closely with the Bureau of Agricultural Statistics. They say that they have their own different computation of the data they collected on the field. And in our office, we also have collected almost the same data, but it will always end up with a different result. And is there a possibility that there should the interpretation of those data would be different from the agency based on their standard method of analyzing the data, or is it generally the same? Is this like it depends on the person who's going to analyze it? Okay, and it is it's because whenever the certain office or the BAS would ask us to collect the data, and they would sometimes ask us to analyze the data collected. But when we submit that data with the analysis to their office, they would interpret it differently, or probably they have a different computation. It will always end up in a different from what could have been a realistic scenario of the situation. I mean, if they would like to ask us to collect the data regarding the rice production, their analysis of the data would be very different from our own analysis. Yes, and they would ask us to have our own analysis of the data, and then they would also have their own analysis of the data. But when the results come in and we would compare it both, it would be very different. And since they said that the authority, I don't know which one is wrong, but since they would insist that they are the statistics office for the agriculture, so we should follow their results. But some of our office mates would react to it because it's not even close to the real situation in the field, based on their opinion.
So in this case, Eileen, you need to prove that you use the right statistic. You need to prove if you believe that you use the right one. You need to prove that why you select this statistic and how you analyze this data, and this is your result that you believe this is true, okay. This is right. And at the same time, if the other one against you, you can ask them how another one analyze the data, and you will see the different. The different result come from different way to analyze the data, okay. And it may be one of you wrong, or maybe both of you wrong. It's possible.
Well, maybe that in that case we would be always wrong because they would present the data
that's
to
true.
the national office, and we cannot present ours because it's only in the local level.
Yeah. Yeah, so Eileen, the best way is find out the like literature review or books or something that you can reference the way you analyze your data. You can tell people, just have you think in your head that how can you tell, Yes, just one more. Just one more. Think in your head. How can you tell people to believe you? Eileen, can you hear me? Think in your head. How can you explain people to believe you? Make people believe you
Yes, I can hear you.
with evidence. Yeah.
Okay. Okay, Session. Okay. Thank you. Thank you.
Yeah. 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 You're welcome. You can ask me anytime if you want. Q&A help you if you would like to pose some question, Eileen. And then now today we have the content for today too. The content for today is about probability estimation, just to and interval estimation. Today, the for module 4. What I would like to tell now, this knowledge is not important. It's about understanding. It's about understanding. If you believe that when we analyze the statistic, we depend on the probability. Which we are doing that when we say this we believe this is the result. It is the right result that come from the probability. That come from the probability. That the basic understanding. Today the topic is about probability and estimation. Probability and estimation for the module 4. For the module 4. But when we work, we will not use this knowledge. We just cross this knowledge because this knowledge is like a background knowledge. For example, when we learn calculus, the way to analyze the number, calculus, we need to know multiple and divide and square. But we will not focus on the square or multiple or something like that. This is the same. When we analyze statistics, we will focus on which statistic that we are going to use to choose to be chosen to analyze the data. That is very important. If we select the wrong one, that wrong from the beginning, so that is that fail. I don't mean you fail the study. I mean the when you do research and you use the wrong statistic, that research will not pass. Will not pass the committee. And today is about the probability and the estimation. The probability is just to tell you like a person, like a percentage that we believe that that the overall event we support that overall event is within one probability, not exceed 1, from 0 to 1. That is the possibility. That is the possibility that some situation will happen under 1, within 0 to 1, within 0 to 1. That is the probability. Normally we say this event may happen about 50%. I just say I expect students come to the session today. It's about 50%. I just say that means about when we talk about the probability, 50 is 0.5. 50 is equal to 0.5. 100 is equal to 1. 0 and 0. So whenever we talk about the probability is between 0 and 1, the chance that something will happen. The coin, when we toss the coin, the chance to appear is about 50 and 50. Maybe head 50 and tail 50 if the coin fair enough. If the coin fair enough, and then the chance to show the head is about 50. It's about 0.5, and the tail is about 0.5. That is the meaning of the probability. Chance for something to be shown. Yeah. The way to analyze, I will post in the video on Monday. I have the video, but I don't want to waste your time now. that how to analyze the probability. It's not difficult. Just the chance that you think will happen, the situation that you think that may happen with the overall the total possibility. Yeah, the total possibility. For example, within 10 days, within 1 year, the car accident may happen about 1,000 times, while the car on the road for 1 year is about million time drive on the road. So the probability to when you drive on the road and you get the car accident is about 1,000 over million. That 1.1 is about 0.1. No, 0.01 probability, something like 1 over 1,000. Yeah. That is the probability, something like this. And then the other topic, I will create a video for you about the probability later. You can see, everyone can see from my portal. And another topic is about estimation. Estimation is when we talk about this, it means because of we cannot collect the data from the population. The population is too much, and then we collect the data from samples. The result from the sample is the estimation. Sorry, the result from the sample is the estimation of the population. Right. We cannot say this is this is the mean of population. Suppose we are going to find out the average mean of age of people in the Philippines. We cannot collect the age of all people in the Philippines, and then we select sample, ask them how old are you, and the sample answer the age, and then we can find the mean of the sample age. And that's okay. The mean of sample age. The mean of sample age, that is the estimate of the mean of population. Mean of sample age is the estimation of the population. Is not the mean of the population. It's not the same. We estimate the population could have the mean like this. Do you understand? The estimation is the way to say how the population look like, to explain how the population look like with the sample. So we cannot sure 100% that if we collect the data from the population, the result will be the same with the result from the sample. So you know what I mean? And then we say something like this. This is the estimation. We need to learn about it because we would like to make understanding, to make everyone understand about the characteristic of the data when we talk about mean or standard deviation or the proportion. This from the sample, all of that is the estimation. It's not the real thing. But we infer to the population. Yeah. And normally when we find out the information, and then we know. So this is the statistic. Mean is mean. So I think you know this already. This mu, this is x bar, and this is variance. This is SD. So this is the variance of the sample, and P maybe P big P. This is small p. Where this is parameter. Parameter is mean something that we use to explain something else. This is parameter to explain the population. This side is population. This one, this group. So this is explain what? The other one. And sample. This is explain sample. Yeah. This explain sample. When we talk about the mean of the sample, we use X bar. We will not use mu. Mu is for population. Explain the population. When we talk about the information in our research, we will use X bar because that data come from sample. And we use SD square to explain variance, of the sample. Of the sample, normally sample has more than one. And the proportion. This is the purpose we analyze this and refer this to population. Refer that X bar mean it could be the same with mu. This is the mean of the sample. We would like to have this. We are going to study this. We would like to know the average age of Filipino people in the Philippines, but we cannot collect the data from everyone. So we collect the data from the sample, and when we analyze the data, we get X bar, and we say that this is the average mean of we estimate this is the estimate mean of the population of the mu. Yeah. So in case of 1 point, you will see in the video that we have point estimation. Point estimation, that means the statistic we estimate only one each point possible mu, just this point. We would like to know if we collect the data from the sample and we found that the average mean is equal to 35, and then the point estimate I am going to show you on Monday. That point estimate 85 is how many the probability, that can be certified. It is linked to the probability that we learned already. The probability is something like this. The possible within here is equal to 1. So the area under here is equal to 1. The area may be difficult to understand, but I would like to just remember now, and you will study more, that the probability, the area of overall under the normal curve is equal to 1, the probability. And when we estimate some parameter or something like this, we will tell people that how many percent, but how many probability that we will get certified. Yeah, something like this. This is the point estimation.
So inferential statistics is the foundation for almost everything we do in introductory and even more advanced stats. So what do we mean by inferential statistics? Well, if you look at the beginning of the word inferential, it's the root infer. Well, what are we doing when we infer something? That means we're making some conclusion or some evaluation based off of information that's not really complete. So we're sort of inferring that something is the case based on the data we have, sort of about something else or something else that's larger. And much of statistics is based around that concept. So in this video, we're going to talk about point estimation. Now, many times in statistics, we're interested in the property of a large population, maybe all the college students on a campus, or maybe all of the workers in a certain industry. Or maybe when we're doing, say, in this example, in this video, we're going to look at statistical quality control. So a product is coming off the assembly line, and we want to check whether or not the quality is good enough. So we select samples off the ends of the assembly line and we check them for whether or not they are within tolerance of our quality control. Now we cannot do that for every product that comes off the line. So we select a sample of those and then we sort of infer that if those are okay, then everything else coming off the line should be okay as well. And that's the idea about point estimation. We're making some estimation about a larger characteristic of a population using sampling techniques. Let's go ahead and take a look at an example. So our example comes from the field of statistical quality control. And in other forms it's called Six Sigma and things like that. But this is a very basic example. So Highway Paving is a company specializing in residential road surfacing. Many of its clients seek out its specialized product, low noise pavement. Recycled rubber can be added to the asphalt mixtures to reduce road noise, which appeals to environmentally conscious clients. So they make this special type of pavement, asphalt, that includes recycled rubber. And when car tires roll over this type of pavement, it reduces the road noise. Not only outside the car, which is good for the neighborhood, but also inside the car as well. Plus, it recycles rubber. And, old tires do not go into landfills. They get chopped up and put into pavement. So it's sort of a win-win. So the product is very popular. Now, one quality of the asphalt is called its viscosity, and that's its resistance to flow. So I'm sure you know about this concept in real life, like oil flows slower than water, and we call that sort of thickness its viscosity. Now, this asphalt must be maintained within very tight limits, otherwise it may be too thick or sort of too watery. So imagine trying to spread asphalt onto a road surface that is really, really thick and you can't really spread it out, or it's too thin and it sort of runs everywhere. So it has to be a certain viscosity. Now, for highway paving, the goal is a viscosity of 3,200. Now, I'm not going to go into the units of viscosity because they're not really relevant and they're kind of weird, so we'll just stick with the number 3,200. Now, during the manufacture of each batch of asphalt, the quality control specialist takes 15 samples of the material and tests the viscosity. This also ensures the batch has uniform viscosity. So, during each batch of asphalt, the quality control person will go into the vat or wherever it's kept and will take sort of 15 measurements or specimens within that batch and test or measure its viscosity. Now, a few things to note here. There's no way to test every single ounce of asphalt, which is the overall population. Therefore, the company must take samples. Now, from those samples, the company must then make inferences about the entire batch. So from these 15 measurements, these 15 specimens, they're going to make some sort of claim about the overall batch. So the inferences made using samples are by definition incomplete. So the 15 samples, what may or may not be an accurate representation of the entire batch. It's always going to be incomplete, but there are ways to ensure that our sampling techniques are good and valid. Therefore, the sample characteristics will always have some error built in. And that's one of the fundamental ideas in point estimation and in sampling. Whenever you're sampling from a larger population, it's never going to be perfect. There's always going to be some error in that estimation. So here are the 15 specimens that the manager took. So in the first specimen, the viscosity was 3193, and specimen 2, 3124, etc. So these are the 15 measurements. The first question is, what is the mean or the average of this overall sample? Now, I will pause here, and I'm going to slap myself on the wrist for doing this. When I talk about a sample, I am talking about the 15 measurements or the 15 specimens, not the individual measurements themselves. And sometimes I slip into those different terms, But when I mean a sample, I'm talking about the total of these 15 measurements. So what is the mean of this sample? Well, it turns out the sample mean here is 3210.73. So 3,210.73. Now it turns out the standard deviation of this sample is 117.61. Now we're not really concerned with the standard deviation at this point and where we're at in inferential statistics, but I just wanted to point that out to you. The thing we're interested here, probably more importantly, is the sample mean of 3210.73. Now that's going to have its own distribution. So here's our sample. This is the curve that represents the sample of 15 specimens. Remember, our sample mean was 3210.73. Standard deviation was 117.61. So the mean of our first sample is down there at the bottom. And you can see that it is X bar sub 1. And that little subscript 1 means that's our first sample. Now remember, the company's goal is a viscosity of 3,200. Now our sample mean was 3210.73. Now since this is a sample mean, we do not expect it to be exactly 3,200. I mean, it could be by the sort of luck, but it's probably not going to be. But the question is 3210.73 close enough to our goal to be acceptable? So the quality control manager has this sample of 15 specimens, measures the viscosity of each specimen, and then comes up with a sample mean of 3,210.73. Is that close enough to the goal to put a check mark next to it and say, yep, this is a good batch? Does this sample accurately reflect the viscosity parameter of the overall batch population? Now, in previous videos, I pointed this out, is that when we use the term parameter, we're talking about the population. So the population mean is a population parameter. Our sample mean is the sample statistic. So parameters versus statistics. But is this sample good enough? Does it overall reflect the whole batch? Now, I know that the answer is yes. But the question is, how can we determine that statistically? And that's going to be something we explore in subsequent videos. So point estimation. What is this overall idea we're trying to get at in this video? What happens is we have some unknown population parameter. That could be the population mean, the population standard deviation, or the population proportion. And again, these are things we do not know. So we're going to use a sample to try to estimate them. Now remember, for the population mean, the symbol is mu. For the population standard deviation, it is sigma. And then for population proportion, p. Now what we're doing is we're going to take a point estimator. So for the population mean, our point estimator is the sample mean. For the population standard deviation, the point estimator is the sample standard deviation. And for the population proportion, the point estimator is the sample proportion. So those are X bar, S, and P bar. So we're taking our empirical data here on the right, and we're using that to make an estimation about some unknown population parameter. Now remember, point estimates are never perfect. They always have some error component in them. So this is commonly referred to as the margin of error, both in statistics and in sort of overall popular culture. So if you watch the polling during a presidential election, at least here in the US, I'm sure it's similar in other places, it'll say this percentage of people agree with this statement plus or minus 3%. Well, that's a margin of error, and this has the same idea. Now, technically, the error component is expressed as a confidence interval. So we are saying that we have some confidence that this point estimator is a proper representation of the overall population. And of course, we're going to talk about confidence intervals in upcoming videos. Okay, so that wraps up this very brief video. That is the beginning of inferential statistics, more specifically about point estimation. I just wanted to get across to you the idea that the foundation of so much of statistics, 95% of statistics, is about taking samples of larger populations and then using those as an estimation of the overall population. Of course, when we do that, they're never going to be perfect. There's always going to be some error involved, but you have to understand sort of how they come about.
And another thing is about interval estimation. Interval is mean the distance interval. Yeah. Another one, we would like to tell people that how many possibility that the lamp will be expired from here. Maybe this is 1 year. The lamp may be expired within 1 year to 2 years. Yeah, to 2 years. This range, this length. So we will say the possibility within this area, how many possibility that the lamp will be expired, the chance that the lamp light bulb like this, the lamp like this, the fluorescent like this will expire, something like this. This is the way to understand the point estimation and interval estimation. The detail I will post on Monday. I will tell you roughly about the idea of this. But this is the basic knowledge. You don't need this knowledge in the exam, in the final exam, because just the basic knowledge for you to understand. This knowledge will bring you to the alpha cut point, critical point in the future. We will talk about that next time, about hypothesis testing. Yeah, hypothesis testing, that we will have the normal curve like this, and then we will say how many percent, how many chance. For example, 95 within here and 505, 5% in. We will talk about this later. This is 0.95, something like this. We call this is 0.05 up here, but in this part is 95% here, 95% here. This is 5% up there. This is the way to. We talk about this next time about the hypothesis testing. The chance that we are going to believe something. If not, we will believe another idea, another assumption. That is hypothesis testing. But these come from estimation. That's why I say the estimation is just basic knowledge that you should know before go further, to make you understand how can you believe the result from the analysis. When you analyze the data, and then you need to tell people that can you believe this or not, how many percent that you can believe the result. If you could like to compare to group of people, and then you say there is the two group of people have different idea, but how many percent you can believe that result? Yeah, how many percent you need to check from here. Yeah, confidence level. We are going to talk about that next time. It's about confidence level, not. But the confidence level is come from this idea. From this idea. If we extend the mu x1 to here, x1 to here, and then we will have the and then we have the area of here. It's about 95 inside, something like this, and the rest is outside. So if the result, if the data that we collect from the sample is out of the range, we will accept another hypothesis. And if within the range, we will accept another one. That is the way statistics work. the way statistics work, to tell people that how can we believe the result, and is it true as we expect? Is it like we expect the result, so that it is different or not, something like this.
All right, let's talk about confidence intervals. This is a huge switch on the way that we think, like what we're doing. Confidence intervals, this is like, it's really cool, but it really, you have to like imagine, this is another thing you have to imagine, like the sampling distribution, you never really make one. I mean, you can start to make one. I guess you could kind of make like a mini one, but the ones we draw, we're imagining taking an infinite amount of samples, sampling and sampling and sampling and sampling forever and ever. This is something else. We're actually, for confidence intervals, we're switching our point of view, and I'm going to show you what I mean in a moment, okay? So let's just make a sampling distribution, and I'll explain to you what a confidence interval is, okay? So here we go. Ready? Suppose 50% of students like tacos. I'd be one of those students. I love tacos. You sampled 25 students. So let's see, what do you think the sampling distribution would be? Well, I know for a fact that the mean of the sampling distribution of p hats is going to be p, and in this case is going to be 0.50. So if I take a sample of 25, somewhere around 50% will like tacos. Oh, let me check my conditions. 50% of this, 50% of this is more than 12. Okay, my conditions are met. The standard deviation of all like this is going to be square root of PQ over N, which would be the square root of 0.5. Q would be 0.5 over 25, which would be the square root of 0.5 times 0.5 is 0.25 over 25. Whoa! And the square root of 25.05 is going to be 10%, 0.10. Whoa! So, let me just double check I got that right. 0.25 divided by 25 is 0.01. The square root of 0.01 is 0.10, 10%. Okay. So we can make a sampling distribution. So if I went out and took samples of size 25 over and over and over again, most of my samples, because 50% of people like tacos, about 50% of my sample, a lot of my p-hats will be near 50%. So imagine all these p-hats. But sometimes I'll have a sample with more than 60%, or less than 40%. Sometimes even less than 30% of my sample will like tacos, and sometimes more than 70% of my sample will like tacos. But remember what this is. This is a pile of p-hats. It's a whole bunch of p-hats. P-hat, p-hat, p-hat. So think of all these p-hats. Okay? And think of a couple. There's a few p-hats I really want you to focus on. I'm going to talk about this p-hat here. Well, first of all, I'm going to draw a very, very, very important line here. This line will be the true p. This is my p, 0.50. And I'm going to talk about a p-hat here, a p-hat here, and possibly a p-hat here. Because it is possible to get a random p-hat here, or even a p-hat down here, and maybe another p-hat. So notice, I could get random p-hats. I could just randomly grab 25, and only a few people like tacos. Even though I know half the people like tacos, it's possible that I randomly grab a group of 25 where not many people like tacos. Less than 30%, maybe 20% like tacos. Just randomly. But most of my p-hats should be within one standard deviation, between 40 and 60. As a matter of fact, 60%, 68% of my p-hats should be within one standard deviation. 95% of my p-hats should be within two standard deviations. Okay? So here's one standard deviation. Remember we used to do this back in the day, back when we was kids. Anyway, got 68% of the p-hats, 95% of the p-hats. Confidence intervals are a little bit different than what we were doing before. We were making sampling distributions, standing at a known p, and saying 68% of my p-hats are between here and here. 95% of my p-hats will be between here and here randomly. And then 99.7 will be within three standard deviations. When we're doing a confidence interval, we don't know the true p. In a confidence interval, we're standing at a p-hat. We could be standing at this p-hat. We could be standing at this p-hat. We could be standing at this p-hat or this p-hat. Even if this p-hat was way out here, p-hat 70, 89, a p-hat of 0.90. Maybe my p-hat randomly was. Maybe 90% of my sample did like tacos. For some reason, I randomly got a group of people who love tacos. We all love tacos. That could happen randomly. But we don't know, in confidence intervals, we don't know what the true P is. So we don't really know how weird our number is compared to everything else. But all we do know is this. We think this way. If 95% of my p-hats are within 2 standard deviations, then, think about this, 95% of my p-hats are within here and here. Then imagine me standing at a p-hat now. If I stand at one of those p-hats and I reach out 2 standard deviations, so suppose it was this p-hat, and I stood at this p-hat, and the p-hat was 0.55. I reach up 2 standard deviations, 0.65, 0.75. I go down 2 standard deviations, 0.45, 0.35. So if I stand at this p-hat, and I go up 2 standard deviations, and I go down 2 standard deviations, what I made was a 95% confidence interval. So if you stand at a p-hat, and go up 2 standard deviations, and down 2 standard deviations, you make a confidence interval, a 95% confidence interval. What that confidence interval is a parameter catcher. You're trying to catch the true P. You're trying to catch this thing. And notice, if you did have this p-hat, and you reached up 2 and down 2, you would capture the true P. And what you'd say is, if you made this confidence interval, if you got a p-hat of 0.55 and you went up 2 standard deviations and down, you'd say this: I'm 95% confident that between 35% and 75% of people like tacos. And you say this confidence interval not knowing whether or not it's actually in there. The true proportion of people who like tacos is actually in there. Because in your mind you know, I don't know what the true P is. All I know is my p-hat. It's the best guess I have. So you could have randomly gotten this p-hat and built an interval from that random p-hat. And if you had, your interval would have caught the parameter. You're trying to catch the parameter. You could have had a p-hat over here. And if you're at this p-hat, let's say 0.62, and you went up 2 standard deviations, 0.72, 0.82, and you went down 2 standard deviations, 0.52, 0.42, you'd say I'm 95% confident that between 0.42 and 0.82, between 42 and 82% of the people like tacos. And that's a good confidence interval. That's a great 95% confidence interval. And that interval from that particular sample, that interval caught the true P that you're trying to get, 50%, which is the true percent of people that like tacos, is in your interval. So when you said it, you're like, I'm 95% confident. You didn't know, but it was actually in there. So you're making these intervals. You're saying, okay, here's my sample. I know it's not exactly whatever my p-hat is for my sample. I know it's not going to be exactly the same as the p. But if I go up and down a little bit, a margin of error. If I go up a margin of error and down a little margin of error, I'm pretty sure it's between here and here, probably, or between here and here. And someone might be wondering, well, why don't you make a 100% confidence interval? Well, I can always make a 100% confidence interval. It looks like this. Well, I'm 100% confident that between 0 and 100% of the population have this quality. You can always make a 100% confidence interval. You know it's between this and this, 0 and all. Either nobody, everybody, or someone in between. Because the more confident you want to get, the wider you have to make your interval. Because I just made a 95. If I wanted to make a 99.7% confidence interval, I'd have to go up 3 standard deviations and down. So I'd go up 10, 20, 30%, down 10, 20, 30%, and my interval would be 60% wide. I'd be saying between 32% and 92%. It's like, I'm more confident it's between here and here, but it's not very accurate. It's like if I'm trying to catch a fish in a pond. Think about what a confidence interval is, a parameter catcher. So I can get like a little tiny net like this and be like, I'm not even very confident that I'm going to catch a fish with a little net like this, like a little tiny net. But if I got a net like this, right, with a big net, right, and I take it, I'm like, I feel a little more confident. I'm probably going to get the fish now. I got the fish. See, so the larger the net, the more likely you are to catch it. We get larger nets if we want to get more confident. The problem is our confidence intervals get wider and they're not as accurate. They're not like right as accurate as we want them. So we know that we could have randomly got this guy, and if we randomly got this guy, we would have caught the parameter also. But the thing is, we don't know which random p-hat. And we just said a minute ago, we talked about it, it is possible for you to go out and take a random sample of 25, and for some reason in that sample, not many people like tacos. And it could happen randomly. And as a matter of fact, about 2.5% of the time, less than 30% of your sample will like tacos. Well, less than, 2.5% of your samples will have a p-hat less than 0.30. So imagine if this was my random p-hat, which could happen. And I stood at that p-hat. Suppose my p-hat was, 0.26, and I went up 2 standard deviations to 0.46, and down 2 standard deviations to 0.06. This is what I'd say. I'd do my study or whatever it was, and I'd say, well, I'm 95% confident that between 6 and 46% of the population like tacos. I did not make a mistake. My confidence interval was created and made perfect. I did not make a mistake. Okay? But I didn't catch the true, 0.46 is right here, the true P. I didn't capture it. So here I am saying, I'm pretty sure it's between here and here, and I'm wrong. And when you make a 95% confidence interval, you're not going to be wrong. You're just not going to catch, which will be wrong, but you're not going to catch the P, the true P, 5% of the time. So 1 out of 20 times you do it. So if you make 20 confident intervals, one of them is going to miss it. So 95% confident means this. 95% of the intervals you make will catch the true P. 5% of the intervals will not. This is what 95% confidence does not mean. Here's what people sometimes say. I'm 95%... There's a 95% chance that the true mean is between 0.06 and 0.46. Well, that's not quite true, because you're making it sound like the true mean or the true proportion. Sometimes 42% of the people, like 42% of the population like tacos, but then sometimes 62%. You're making it sound like the parameter is moving around. Sometimes this many people like tacos, and so the parameter is out there. It's here. What's moving around is the confidence intervals. So your confidence lies in the interval, not or in the many intervals. So when you're 95% confident, you know 95% of the intervals. Okay, this interval I'm only 95% sure, because if I know I made a bunch of these intervals, only 95% of the intervals would capture the true P. Because notice this P is here. It depends. The p-hat, every p-hat makes a different interval. 95% of the p-hats will make an interval that catches the true P. 5% of the p-hats, you'll make intervals from that, and it won't catch the true P. Here's another mistake some people say. 95% of the p-hats are between this and this. No, you do not know where 95% of the p-hats are. You don't even know where your p-hat is with respect to the true P. Suppose you had this p-hat, 0.90, and you went down 2 standard deviations, 0.70, and up 2 standard deviations, whatever. Are 95% of the p-hats between here and here? No. Maybe only 1% of the p-hats are in your confidence interval. You have no idea where the p-hats are. Here's the deal. You're standing on some p-hat, and you're like, I'm going to go up a little bit, I'm going to go down a little bit, I hope it's in there, and you don't know if it's in there, but you just, maybe, and you're going to be wrong sometimes, but they like it. You make a 90% confidence interval, you're going to be wrong. You're not going to catch the P 10% of the time. So when they say, what do they mean by 95% confident? You say, if I made a bunch of intervals, or if I took a bunch of samples of size, whatever it is, and made intervals from all those samples, 95% of my intervals made this way would catch. 5% of my intervals wouldn't. Okay? What does it look like? The formula look like? Well, it's exactly what we're doing here. It's pretty straightforward. It looks like this. For a proportion, it looks like this. I stand at my p-hat, and I go up and down some margin of error, right? I go up 20%, down 20%, and hopefully, 2 standard deviations, up 2 standard deviations. So it's just some p-hat, plus or minus some number. In this case, we did 2 standard deviations. And we know in our case here, standard deviation is square root PQ over N. And 2 is just the z-score. 2, the reason why I went down 2, I went from a z-score of -2 to a z-score of +2 is, I went up a number of standard deviations. A z-score is the number of standard deviations away from the mean. I went up 2 and down 2, so the z-score I used was 2. So really it's just up some z, and that's called the critical z. So you stand at your p-hat and you go up some number of standard deviations. If you want to make a 99.7% confidence interval, you go up and down 3 standard deviations. If you want to make a 68% confidence interval, you go up and down 1 standard deviation. Nobody makes those. And what happens is, when you want to make this thing, sometimes people are like, wait a minute, we don't have P and we don't have Q. We don't have the true P. So you think, what's the best guess at the true P? You use the p-hat. And you use the p-hat here and the q-hat here. And this is the formula for it. This is now called the standard error, but whatever. Anyway, this is the formula for a confidence interval. You stand at some p-hat. You reach up a couple standard deviations, down a couple standard deviations, and hope you catch the true P. You might not catch it. The thing is, you don't know. You'll never know. Get used to it. That's what statistics, like what we do, is we just kind of say sort of what kind of might happen, we hope, or think could.
So today, the basic knowledge that I expect everyone to know is about probability. You need to know the meaning of probability. That if you cannot understand now, don't worry. I will post the detail. I have video for you on Monday. And then the estimation, point estimation, just only 1 point. How many percent that something like this will happen within this situation, and interval estimation, that if it's like a period of time or something like this, how many percent that this situation may happen, something like this. Eileen, do you have something?
No, I'm perfectly okay, Sir Sean. I think I have so far understood what the meaning of probability is.
Yeah, that's basic knowledge.
Yes, Sir
Basic
Sean.
knowledge. How about you, JR? Yeah, JR, is it all right? Cannot hear JR. Sorry, JR, I cannot hear you. Really?
Hello, sir. Could you hear me now? Hello?
Oh, yes, I can hear you now.
Yeah, I'm okay with the discussion. My only concern is sometimes the video is freezing, so that's my only concern, the video. But with regards to the discussion, I'm okay.
Okay, JR. But Michelle, you need to see my video on Monday. Okay.
Yes, sir. We would.
But I miss Roxanne. Huh? JR, you have something?
Yeah, we'll appreciate the video because there was an audio problem a while ago. We cannot hear what you were discussing. There was a part that we cannot hear, sir.
I think I will create a video, and if something lost, I will fill it up. I will explain more. I will check the record, and then I will fill up something if it's lost.
Okay.
You're welcome.
Thank you, sir.
So, Michelle, I can see your thumb. Could be all right. And now, how about us? You can ask me now because I'm going home on Tuesday. On Tuesday the 30th, I'm going to Indonesia first, and then I go home next week. Yeah. I give you the situation and data, and I ask you to think about how you can answer my request. I mean, I will ask you to find out first how can I know the differences between two cities, the opinion from two cities. I will tell you this is the opinion from the Manila, this is the opinion from Los Baños, and I would like to know the different idea from two cities. something like this, and maybe more than this, and then I provide you the data, the number. That's all I ask you, and then you need to think how can you analyze the data and show me the result, explain like if you see the research, you will see some chapter that they explain the result of the research. I would like to see something like that, but not thing that you cannot explain. For example, the literature review, I don't need that, because at that time to me it's about statistics. So I just would like everyone to select the right statistic, use the right way to analyze statistics. Yeah, use the right way. You need to explain the way you do your analyzing. But I will post the criteria. I will post the criteria what I expect from you, the criteria, and how can you get the mark 70%. How can you get that each score? I will post your criteria. Wait a minute. It's a Rubik. Oh, no problem. I feel it up. I will create the rule. Michelle, Eileen, you talk something?
I think that's a permanent marker.
Not my fault. Not my fault. Someone prepared this for me. Another one.
I just
the red color.
I think that's a permanent marker.
The same brand. The same brand. Okay. Okay. I am going to create the table like this. I am going to create the table like this for the final exam, and then I explain this is the purpose. This is the purpose. Suppose adjective one activity. This is the purpose activity. For example, you can analyze the data. You show me the result. So, for example, you analyze the data, show the result, probably make the conclusion right or something, and then I explain how is it look like, and this is 5 mark. How is it look like? This become 10, and how it look like this become 15, something like this. You know what I mean? I will do this nearly the end, before the final exam. Explain everything. This is the explanation, the behavior that I would like to see, the result that I would like to see itself. Yeah, I will explain you like this. And if you can check yourself. You can check yourself. For example, this is activity. Can you use the right statistic, and then you can check if you use the right procedure or something like this. And I will tell you the detail here. I will write down the detail in each cell here. How can you get 5? How can you get 10? How you get 15 or something like this? And I believe someone will get 70. No problem. I do not tap about the score. If you do the right, you can check here. You can arguing with me. If you think you should get 70, and I tell you have got 60, we can negotiate. We can talk. I do not mind about that. I do not mind. I'm fair. Don't worry about that. We have criteria here, and then you check yourself. You pass this. You pass this point. You pass this point. From this activity, you should get 70. I will. If I give you 60, you talk to me. Yeah. If you right, I will change. Don't worry. Yeah, but I have my reason. I will tell you. Did you get 15? Did you get 10? Did you get 10? Support. Yeah. And I talk to you. No problem. I will explain you something like this. Yeah. You can see now the purpose. Actually, I post it already that I expect you to do something in the like a study schedule shame or in that on my portal now. But in the last week, I post that already. But I didn't do this Now, that is the activity A, B, C, D. Yeah, then I expect all of you. And I believe if you can do this when you do your research, you will like imply the knowledge to the real situation. You have experience how to analyze your data, the real situation. That is my expectation. I want all of you to do your analysis by yourself if you can, and you need program. If possible, everyone, I would like everyone to install the program in your computer now. Maybe last time, who go to the mountain? Jebet text me, message me that he would like to have exercise about the statistic analysis. He would like to have some number, some data, and he would like to try to use the program to analyze. That's good intention. And I recommend him to see some video, and I will provide him. He requests me the data, and he would like to check if he can do that. So before you finish MLM 281, you need to install the program. From the beginning, someone asked me if the version is necessary. No, not necessary. Any version, SPSS, and I tell you more. Any program you can use. I need the result, and I check already that even you use different program, the result will be the same. Any program, statistic program, we have the same result. So I do not mind if you would like. Eileen, if your friend who have got a different result, use the different program, don't believe him or her. Eileen, can you hear me? Yeah. Yeah, right, Eileen. The same result. I test that already. So in my class, I do not mind if you would like to use other program to analyze the data, or you can use calculator if you can. I have no problem.
I think I will.
You explain me. You use
Yes,
calculator.
I think I will. Or I will show him
and show
the
me
program,
how.
so we will have the same result. Yes.
I think that's all for the lecture. The rest is about eating. You want to eat something, Eileen? Oh, we have something. Where is it? Well, please give me. Yeah. This one, Eileen. Hey. Have you eaten this before, Eileen?
Yes, I want.
Eileen, have you eaten this before?
I want to see Sir Sean how you eat the balut.
Have you eaten
At least before we end
before?
the discussion, we can see it.
So
Yes.
I think it's enough. And where are you now, Eileen? I think it's enough for you too.
Sir Sean? I try to eat.
I think
Yes, I
ATM
have. Yes, I
provide
have.
this
But I really prefer
for
the
everyone,
balut
and that
than
includes
the
you.
balut itself.
Yeah.
I am in Biliran province, Sir Sean.
Okay, I now who have the question about the
Pardon, Sir
studying. You can ask me anything about studying now, including you, Eileen. AKM, JR.
Yes, it includes
Yeah, I
me.
will eat later.
My husband tries.
I
Let's
am
me.
making decision, Eileen.
My husband wanted me to eat as much balut as I can.
I am going to die or not. Yeah. Huh? Say that again. JR, what do you say? Ah. Okay. Okay, about the studying.
Michelle
If anyone have the
says
question,
like
you can post it. You can post it in Q&A. Q&A anytime. Yeah. But now, if you don't have that,
The
you
Michelle
can
wants to
talk
eat
something else.
balut.
Eileen, who Who are you going to
Balut
talk to?
eggs.
The
Now is
balut
the
is rich
private
in
time.
protein. That's what I said.
You can talk to your friend. I have 1, 2, 3, 4, 7 friends here.
It's rich protein, sir.
Michelle, nobody hear you. Nobody can hear you, Michelle. Sorry.
Yes, Sir Sean.
Yeah, I can
I
hear
have
you
my
now.
questions already.
Not only me, everyone can hear you. Wow. You win. Okay, you can talk to your friend in your room, in this room. Roxanne, we are waiting for Roxanne.
Now
We are waiting for
now you can
Roxanne.
hear me. Everyone also hear you, Doc Chan. I put on loudspeaker.
Yeah. You want to see everyone eat barod, right? Right, Michelle?
Who will dance for
One,
today, Doc
yeah.
Chan?
1 barod for each. Yeah.
Is there any intermission number?
Yeah, I think okay, we have
Roxanne
enough.
will show us a headstand.
Yeah. Michelle,
So is there gonna be video
I think-
key session too
I think
while
friend-
we are watching Sir Sean eat the balut?
friends are going to follow
Cheering
your
session.
idea, your request. Friends here.
Oh, it's for everyone. So everyone has
Ah.
one balot each.
Yeah.
Cheer.
One
Yes.
balut.
Yeah, one balot for each. Yeah, one balot for each.
But
Yeah,
what happened to
kampay.
the inutak? What happened to the inutak? Parang naubos ah.
Oh, it's time for balot.
Wait. Something wrong. Wait.
Doc Shan. Cheers. Come on, cheers the balot. Okay, cheers for the balot. I'm so brave because I'm not there. I don't eat balot.
I only eat the penoy. I cannot really dare to eat the chick itself, Michelle.
Yeah.
You have been